Hello and a very warm welcome to Kognito Key. Today we're going to pull back the curtain on a tiny, unsung hero of the electronics world. We're talking about the JFET. Think of it as the microscopic traffic cop that's inside pretty much all of your favorite gadgets, directing the show. I mean, have you ever really thought about it? What is it that controls that incredibly complex dance of electrons that makes your phone, your laptop, and everything else just work? Well, the answer is this fascinating little device, and today we're going to figure out exactly how it does its magic. So let's dive right in. Okay, so let's start with the absolute basics. What in the world is a JFET? In this first part, we're going to break down what it is and what makes it tick. So JFET is short for Junction Field Effect Transistor. At its core, it's a semiconductor device with 3 connection points, or terminals. But here's the key takeaway. Its entire job is to be voltage controlled. That means you use a very small voltage to control a much bigger flow of current. It's also called a unipolar transistor, and that's just a fancy way of saying it only relies on one type of charge carrier to get the work done. And that brings us to the 2 main types of JFETs. You've got your N channel and your P channel. The big difference is what's actually carrying the current. In an N channel, it's electrons, which is pretty straightforward. But in a P channel, the current is carried by things called holes. A simple way to think about them is like bubbles moving through water. They're basically just empty spots where an electron could be. And as these spots move, they create a current. Now, every JFET has 3 of those terminals I mentioned, and thankfully, their names make a lot of sense. You have the source, which is where the charge carriers, the electrodes or holes, enter the device. They then flow through a little pathway called a channel to the drain, which is where they exit. And then you have the most important part, the gate. This is the control knob. The voltage you put on the gate is what opens or closes the flow of traffic. Okay, so we know what it is, but how are these tiny little gatekeepers actually made? Understanding how they're built is really the key to understanding how they work. So let's picture building an N-channel JFET from scratch. First, you take a small bar of N-type silicon. That's our base. Then you create 2 little P-type regions on opposite sides of it. The N-type material that gets squeezed right between them becomes our channel, the pathway for electrons. And finally, you connect those 2 P-type regions together to make the gate, and then just add metal contacts at either end of the channel for the source and drain. That's it. So simple, but so effective. All right, now for the really cool part. How does this little thing actually control electricity? We're going to look at 3 different situations to see this tiny traffic cop in action. So first, what if we just leave it alone? With 0 voltage applied to the gate, there's this naturally occurring thin layer called a depletion region, where there are no free charges. But it's tiny, so the channel is basically wide open, and electrons can flow from the source to the drain with no problem. The light is green. Now, this is where it gets interesting. What happens when we apply a small negative voltage to the gate? Well, that voltage acts like a force field, pushing back and causing those depletion regions to grow wider. This starts to squeeze the channel, making it narrower. It's now harder for electrons to get through, so the flow of current goes down. We're starting to close the valve. And finally, what if we really crank up that negative voltage? As we increase it, those depletion regions just keep expanding until they actually touch each other, completely pinching off the channel. At this point, no electrons can get through at all. The current drops to 0. The gate is completely shut. It's a perfect illustration of how a simple voltage can act like a perfect on-off switch for electricity. And that exact voltage, the one that's just enough to completely stop the flow, has a special name. It's called the pinch-off voltage. It's that critical point that turns the JFET completely off. And having such a precise voltage-controlled off switch is what makes this device so incredibly useful. So that's all the theory, but why should you care? Let's take a look at the real world to see what makes JFETs so special and where you can actually find them. Of course, like anything in engineering, JFETs have their pros and cons. On the plus side, they produce very little electronic noise, which is fantastic for things like audio equipment where you don't want any extra hiss. They also have a super high input impedance, which basically means they can measure a signal without messing it up. On the other hand, they can be a little more expensive, and they're not always the best choice for amplifying a huge range of frequencies all at once. So where do these little traffic cops do their work? Well, you'll find them right at the heart of digital circuits, acting as super fast on-off switches. Because they're so low noise, they're perfect for amplifying really faint signals, like in a radio receiver. You'll also see them in all sorts of other circuits, from operational amplifiers to the tiny memory cells inside your computer. So you see, the JFET isn't just another component. It represents a beautifully simple and elegant idea, a gate for electricity that you can control with a voltage, not with a physical switch. It's one of the most fundamental building blocks of our digital age. And it really gets you thinking, right? What other amazing things can we build on this one simple principle? And that wraps up our look at the JFET. I really hope this explainer helped you understand how this amazing little device works and why it's so important for pretty much all the electronics we use every day. If you enjoyed this and learned something new, please subscribe to Kognito Key. And don't forget to hit that like button and share this video with anyone else who's curious about the magic hiding inside our devices. Thank you so much for joining us, and we'll see you in the next one.